Oh, that's good. Well, welcome. Welcome to this session called Machine Learning in the Real World. As I'm not part of the circus, I thought I should just use a few minutes introducing myself. So my name is Karsten Strøbæk. I graduated from the University of Copenhagen in '95 with a master's in economics and econometrics. I did my master thesis on the mathematical properties of artificial neural networks. So if you can't sleep, let me know and you can get a copy. At that time, I suppose that's what we call machine learning today, right? So you could argue that I was very forth-seeing, but that's to be. For the last 12 years, I worked at Microsoft doing stuff within IoT, primarily within manufacturing and stuff that moves, so auto and vessels. And all the boring stuff that doesn't really demo well at Igniter built. So I don't have one Blinky, but if you have 1 million in 200 factories across 5 continents, then we can talk, right? So that's I guess what I tinkle with when I'm not standing here. I did this talk a couple of years ago at an internal Microsoft conference, and the working title was MLMA, which is an acronym for Machine Learning My Ass. And the abstract went something like this. Have you ever been in a customer meeting where after the customer has told you their problem, the salesperson turns around and says, "You just need machine learning. Then this is a session for you." I got a mail from my boss's boss or something high up saying, "Karsten, I hope this is a joke. We don't swan the titles. We don't make fun of sales, and we don't diss our machine learning initiative. But apart from that, it's a great idea." So, back to the boring title, Machine Learning in the Real World. Experiences. And a disclaimer. So if you are sitting here because you have hoped to see how to deploy an end-to-end machine learning solution, you will be very disappointed. Also, how you maintain your hundreds of models and how you retrain them, etc., etc. That's not really what this is all about. This is a talk about what happens before you get to the cool algorithms, right? So I won't get offended if you stand up and walk away. It's an hour you will never get back, so now's the time. Okay, well, let's continue. A small agenda, couple of points. So I'm going to spend a little time talking about data quality of statistics, something about time, something I call physics. If we have time, I will try to talk a little bit about a real system, predictive maintenance anomaly detection system that I created for a small wind turbine producer in Jutland. There will be quizzes and prizes. There's some advantage for working at Microsoft, right? So, yeah. So at least that's also maybe my attempt to make you stay awake. A few other words about the agenda. So when I did the talk last time, one of the comments was, "Where's the red thread?" Well, yeah. No, but seriously, so all of the examples are things that I have experienced in real customer engagement, right? Real customers paying real money for this shit. And hopefully you can avoid some of the things that I experienced. So that's like the breadth. We will cover, time and statistics, and it's going to be a broad topic selection, but yeah, real life. So let's dig into it, data quality. And a few subtopics here. So missing data, incorrect data, something I call precision accuracy. Then we're going to look at averages and conditional probabilities. The last two because I did a small survey at the Institute of Economics some time ago, and if there are two things people cannot do, it is averages and probabilities. So I will test you, my dear audience. So missing data. One of the challenges that we have is that data may not be when we need it. And if we're looking at some IoT device, we can have the saying that, oh, okay, I mean, it's probably going to wake up and data is gonna come eventually. I mean, that's one strategy. But regardless, then from a mathematical point of view, you have this thing, can you extrapolate? So there's something you know, and there's something you don't know. And can you extrapolate from one to the other? And some years ago, I did a project for a credit card company. And apart from supplying credit cards, they have these, in Danish we call it like quick loans. You know, Bob goes into Radio Shack, wants the 62-inch OLED television, but can't afford it. Goes to the counter, fills out a form, in 15 minutes he walks out the store with his television. Quick loan. The competitive advantage of these companies is that they must say yes. Because if they don't, Radio Shack doesn't actually sell the television. And if they say no too much, they find another provider, basically. On the other hand, the credit card company is somewhat interested in Bob actually paying back. So it's not like they want to. So let's say that the orange spots, that's all the people that they actually provided loans. And they know tons of stuff about them. But under the line, that's all the people they rejected. They don't know anything about them, right? Because they didn't give them a loan. So they don't have the address and credit history and et cetera, et cetera. They don't know anything about them. So can we extrapolate from above to below? And there are all numerous statistical things you can do to see if you can do something like that. The company actually had a really cool, I thought, solution to this. For a month, they said yes to everything. Of course, they didn't announce that, obviously. So for a month, I mean, every person walking into the store wanted to buy something, that wanted a loan, they got it. And suddenly all the blues turned into oranges, right? So I'm not suggesting that that's a feasible way of doing it, but it's one way to ensure that, and just because we use machine learning, we still have this problem. Remember that. Another situation is that there's a small company in Jutland that create pumps. If you have a house or you live in an apartment building and you have hot water at the top, you probably have one of them pumps in the basement. And apart from creating the pumps, they have certain solutions, and one of them is a solution where they monitor wells and see if there's a risk of flood. So in these wells, they have these pumps, they send data through by these different gateways to the headquarter, and using that data and weather forecasts, they try to predict if there's going to be a flood in your well. And the company was very, very adamant that, oh, no, we need like 1-minute updates because that's really important. Oh, that's interesting, but these may be offline. Yeah, no, we need 1-minute updates. And when you kind of ask them, and why do you need 1-minute updates? That's because when Bob created the model, he used 1-minute updates, and he's left the company, and we actually no clue what's going on. And again, well, I mean, that's probably not the best excuse for not changing anything. I think a more interesting question would be, both from a statistical point of view, but also from a business perspective, how much data is enough for you to actually make decisions? Can you live with 80%? 85%? I mean, again, last time you did a project, when did you actually ask business? I mean, what confidential interval is okay for you? I mean, how much can we squeeze it? And it's not about 1 minute to 10 minutes. It's a more fundamental question of how much data is enough, because we will never have all of it. So, I mean, we can also talk about like stale data. If we don't get an update, is that because there hasn't been one? Or is it because it's a disconnect? And there's numerous ways where we can try to fix that. But it all comes down to when is enough enough? I suppose I should say that if you have any questions, please feel free to interrupt me, or if you don't understand my English, same goes there. Incorrect data. It's kind of a cousin to missing data. The reason I'm showing two keyboards is that in the good old days when we did surveys, people with clipboards running around asking people questions, going home to the office, typing in the answers. Research has shown that even if you have two people keying in precisely the same stack of papers, you get between 2 and 4% errors. And I guess these days we don't. Seldom we type in. We have maybe devices. The aforementioned pump company has a dormitory in the harbor in a city called Aarhus in Jutland. There's about 150 apartments where students live. And in each apartment, there's about 20 sensors. So you can measure temperature, humidity, CO2. Some of the devices are flow, some of them are pressure, etc. And they asked, it would be really interesting if we could make some analysis seeing do the west-facing buildings use more energy than the east-facing buildings? And it's a difference between the first floor and the fourth floor, etc. Yeah, that sounds like a good idea. Do you have any historical data so we can create the model before we actually get the live data? Oh yeah, tons of historical data. Oh, okay, fair enough. We began to look and said, oh, okay, so these observations where it claims that there's like 200 degrees in the dormitory, well, what should we do about them? Yeah, okay, yeah, but let's. And then these where it says that the humidity is like 2007, but yeah, okay, that might not so. And then the negative CO2, yeah, okay, I'll go there as well. So again, just saying, and you know this, right? But just because you have a lot of data doesn't mean that you have a lot of information. And do yourself the favor of actually looking at what you have and making some kind of validation, because garbage in, garbage out is also true for machine learning or deep learning or all the other marketing BS that companies like my own is trying to convince you about. So, okay. Before moving on, I have to ask you a question. Anyone with a medical degree in the room? Doctors? Any doctors? Anyone related to doctors? You don't count? Okay. Just a few. Okay, I'm gonna pick on them. My father's a doctor, so I'm allowed to. I'm gonna pick on them. So it used to be that in the good old days, the Danish newspapers would publish the results of the math tests from first-year medical students in Denmark. That was like reading the comics, man. I mean, that was like, they can't do math if their life depended on it, right? and I especially remember one assignment where the question was something like, calculate how many, the amount of active ingredients in each tablet, something like that. And the coming doctor found that, it should probably be 1,000 kilos. And I don't know about you, but I mean, I don't think even an elephant would be able to swallow something like that, right? So you would probably step back and say, yeah, maybe that's something with the comma. I mean, maybe it shouldn't be kilos, maybe it should be milligrams or whatever, right? But it's this missing reflection or contemplation of your results. And maybe it's just because I'm getting old and gray, but I seem to see that it's something that gets worse each year. Yeah. I'm not old and gray and grumpy all the time, trust me. So for the predictive maintenance system that I will hopefully talk about at the end, we had to do some SQL queries. And one of my dear colleagues tasked with doing one, and it was do something group by ID. I was like, whatever it was. And then when she was done, she asked, "Can you check if it's, does this look correct?" I said, "I can do that." And all IDs were 20. And again, might be the case. Who knows? I would probably step back and say, why not? Okay, if the assignment is by ID, that's probably the reason why we do that. And of course, it turned out that there was some stupid mistake, and that was good, and we got it fixed. But just, again, take the time. Look at what you get and see if it makes sense. Unfortunately, fall into this Dunning-Kruger trap, right? We don't know what we don't know. So even though I ask you to be skeptical, please don't be, I was going to say stupid, but that's probably a wrong word, but, and leads to this. So many years ago, a group of Danish engineers from D2, or whatever it was called at that point in time, sat down and tried to model a way that hulls and vessels should look like to minimize the water friction. And they made a model, and it came up with this strange hump. I said, it's like, no way. So they changed the model, and the hump looked slightly different, but it was still a hump. So, okay. And I guess back then, we couldn't 3D print, so they probably had, I don't know, somebody to actually make a model. And I guess you don't use wind tunnels if it's a ship, so I don't know, a water tunnel, is that the word? But it actually turned out that that thing decreases, it's like amazing what it does to the friction, meaning less bunker, meaning more margin. And of course, if they had just been completely, this is just too far out, then we had never actually discovered something like this. So be cautious and critical, but don't be completely, don't listen to your instincts necessarily, right? But if the math is good and you have second pair of eyes, etc., you might come up with something like this. And then most vessels actually now look like this because of some really intelligent chaps in north of Copenhagen. And it has to do with the difference between precision and accuracy, right? So precision is basically, how many decimals places are at the end of a given measurement. Where accuracy is, how close is it to the real value. And people tend to confuse these two things. Because you can be very, very precise and very not accurate. Because what we ideally want is the precise and accurate. And then, I'll let you decide where you want to be if you can't be in the top corner. But it's not the same, right? It's not the same. It's two different things, and we have to acknowledge that it's two different things. And now time for a quiz. I will dive into my bag, and I will see this really nice umbrella that you can win. So we have something like this. We do a lookup into a SQL table. The value happens to be stored in a character field, so we need to cast it to a double. We add it to the list, and we calculate the average. Why should, I know, all the checks and shit and guard clauses. Why is this a really bad idea? Yeah. That's not quite right. Almost. Yeah. No, okay, there's like a loop. There's a loop here, right? So I didn't. So we loop for the lookups. Yeah, sorry. I should say that we loop around the lookup and then we do. So yeah. So otherwise you would have been right. Yeah. No. Yeah. No, it's actually really simple. What's the default of a double? 0. So if we do a loop 100 times and 20 of the observations are my name, what does that do to the average? It's skewed, right? Oh, you're the first one, so you get the umbrella. You can trade it. It's really nice. So again, I know you probably, I mean, in real life you would never do, well, it actually happened in real life, but it shouldn't happen in real life. Let me put it that way. So again, something simple like that. It doesn't break because you have a nice try, but it gives you a 0. And that's not really what you want. At least if you do, maybe you should, I mean, then you should maybe when you calculate the average, do it differently, etc., etc. Okay. Sums. We have a decimal, we have a character, we try to parse it, we try to add them together. What is D? It's not rocket science. Nope. Okay, C#. Doesn't really matter. Shit, American, fair point. Ah, history, yeah, okay, so this is an American example, C#, trying to cast 1.1 as a string. What do we get? Something like 2.2, yes, exactly. Like an off-eye notebook, sir. Again, you can throw it after your cat if you don't like it. Okay, next one. We have A is 1.1. It's still American. It's still C#. And B happens to be A. What is the result here? Yeah, who said that? Exactly. 1.1. There you go, sir. I have 2 pairs of socks if you rather want socks. So, okay. Yeah, but it's beside the point. That's not really, yeah. How about the last one? Yep, sorry, guys. Because somebody at some point decided that the characters of the name is an okay value, meaning not a number. So D will be a double, meaning not a number. Again, didn't know, you'd be potentially screwed. Okay, let's move on to the conditional probabilities. If you know the Hunty more, please, stay silent and let the rest of your audience. So it goes like this. I'm the game host, and you are the participants, and there are 3 doors. Behind one of them, there's a nice prize, like a Maserati, nice Italian sports car. Behind another door, there's nothing, and behind the 3rd door, there is a goat. So you select one of the doors, and let's say you select door number 1, because then it fits with this next slide, right? Okay, so you have selected door number 1. I will then open a door you have not selected. 3, and show the goat. And you now get the option. Do you want to stay with your initial selection, or do you want to swap? So that's like, yes, sir. You're absolutely true. And of course, it may, when you look at it, say, come on, 50-50. But that's the thing about conditional probabilities, right? You have to take account what it is you know, and you're absolutely true. But let me try to illustrate it. So what if we don't have 3 doors? What if we had 60 doors, 1,000 doors, or 1,000,000 doors? And you select one, and I open all the, it took quite a while to get the goats in the room, so if we had to, I open all the 999,998. And now I ask you, so do you want to stay with the one you selected initially, or do you want to swap? What do you want to do? Yeah, because the chance of you, it's, again, from a mathematical point of view, it's not quite the same. But from an illustration point of view, I actually thought this was quite cool. So it's exactly. And then you can ask, what the f is he talking about, conditional probabilities? But it leans into the difference between, or the thing about causality and correlation, right? It may be that Google can tell us that a flu epidemic is on the rise, but they can't tell us why. I was almost going to say COVID-19, but that would have been a bad joke. And just because we're using machine learning, and especially because we're using machine learning, we have this problem about causality. Good old traditional statistical models, you can freaking see what variables you have and you can calculate. And I'm not saying you can't do root cause analysis with deep learning. It's just really, really hard. And again, I mean, you've probably seen this, right? I mean, I'm sure there's about 120 people that looks forward to Nicolas Cage going on pension, so they're not gonna drown. Or another one of my really favorites, and I really like cheese, but I'm kind of being afraid to. Maybe I should find somewhere else a hammock or something like that. So correlation and causality, it's two different things. It means a lot, and you can, we're probably not going to ban the selling of cheese just because of this, right? So be careful. Moving right along. So time. Time is a strange concept. And don't worry, I'm not going to tell you, spend a lot of time on the philosophical debates about what time is and what time is not. It's going to be a lot more concrete than that. So in the good old days, it was noon when the sun was highest, and that's when the bell tower chimed. Easy peasy. That was easy. And the problem, of course, is that this is where we are, Copenhagen, if you've forgotten. And if we take another small town in Jutland, or the big one, Aalborg, there's actually 15 minutes difference. And that's a small country like Denmark, right? And you could say, well, 15 minutes. But in the mid-1800s century, when the railroads began to be laid out, the time schedules, again, now we assume that back then the railroads actually kept the schedules. I know that, but let's assume they do that. The schedules were, of course, in Copenhagen time, meaning that all the people in Aalborg would actually miss the train. So that then led to the concept of time zones. So it wasn't actually until 1878 that a Canadian, Sir Stanford Fleming, came up with this idea. The US railways began to use it in 1883, and in 1884 there was the first International Prime Meridian Conference. And that was where it was decided that all around the world we should use something like this. So, and then you would say, from this point in time, determining what time is and where you are is easy. So, I did a project for a cruise liner. Still waiting for, they don't hand out, look at me, I hand out free stuff. I'm still waiting for the cruise to Caribbean or whatever. How do you determine what time it is in a ship in Indian Ocean? So ships sail in something called corridors, like planes need to fly in corridors, and these are set in local time. And if you breach them, I don't know, some marine ship will come along and sink you or whatever. But it's not, at least a lot of bells will probably go off in the control tower. And contrary to what my colleagues are telling you from the Azure map division, you can't actually determine the time zone from the GPX coordinates. The reason being that time zones, and especially summer winter time, is often decided politically. As an example, it used to be that, I don't know if it's still, but it used to be that Russia each year determined if they wanted to use summer winter time. And again, how do you create a system based on if Oleg pushes a button or not? That's gonna be hard, right? And in this specific instance, what we wanted to do was basically determine when does the voyage end? Because when that happens, we want to download tons of data from the ship, but when it's sailing around, as I said, internet connectivity isn't great, and it often has to be shared with Mrs. Jones on Facebook with the grandchildren or whatever, and she's get pissed if she can't get connected. So most of the data is collected, and then when the ship is in shore, it's how do you determine that now we're done? Again, if you don't have somebody press a button. And you say, yeah, geofencing. Yeah, but as I said, that doesn't really go with the corridors and stuff like that, right? So it has to be local time. Yeah? Yeah, but yeah, it could be something like that. But what's the big storm and the mite and things? And so we thought about geofencing, but then if the harbor is full, they need to anchor in the bay, and then what if the ship is standing still? But maybe it's a combination. I'm not saying it can't be solved. I'm just saying there's not necessarily an easy way to do it. What the company did before we kind of came along was that they waited a week and hoped for the best. That's one way of doing it. So time is just, pain sometimes. So again, sometimes you need to be creative. Sometimes you need to do a multitude of things. It could be, as you say, engines off, close to scheduled arrival time, weather is nice, etc., etc. So there can be a multiple things. So now let's change to something else. And yeah, physics. And then I don't know, but if you're from, there's been quite a lot of debate recently about a certain radio program in Denmark, some flat earthers, and I'm not saying that the Earth is necessarily flat, unless, of course, that you happen to any Terry Pratchett fans in here? Oh yeah. Right. So unless we actually are on Discworld on Greater Toon flying through the universe, our Earth looks like. And we have this general problem of going from a 3-dimensional world to a 2-dimensional world. A bit like going from digital to analog to digital, vice versa, if you're in mechanical engineering. So depending on what you need to do, you use different kinds of projections. So some of them are what we call angle true, or the angles, and some of them are called like distance true. I don't know the English term, but that's like literally translated from Denmark, right? So, and again, it can be illustrated from this. So depending on what projection you use, you get your head squashed in different ways. And what that leads to is problem of long legs. And no, I'm not talking about your partner here. There's nothing sexual about it. But as I mentioned before, we have a corridor. And we have a ship. And said ship needs to sail inside that corridor. If the corridor gets too long, from a mathematical point of view, it's going to look like the ship sails like this. Which I can tell you, if you're sitting in a control room, monitoring if ships leave the corridor, all hell breaks loose. So again, and this has nothing to do with, if you're using TensorFlow or Zola models or whatever hosting system you have, this is because the Earth happens to be round and you want to go from one projection to the other. I can try to illustrate it a little differently. So we have the Earth. We want to go from point A to point B. And unless you're a submarine, you can't really go straight arrow way, right? You have to do it like this. And that's basically the problem. And then, again, I'm not saying it can't be solved. Yes, you could make the leg smaller. I mean, that would be the obvious selection, right? And then there's also all kinds of other tricks you can do from a mathematical point of view to limit. But if you don't know, you have it, it looks really nice because we are testing, I don't know, using, it used to be the ship between across Storebælt, and so let's say from here to whatever. It wouldn't be a problem. But in the real world, it actually is. So again, be cautious of what you do. And we have another quiz. And so this is so now we actually want to know where the ship is, and we want to track the position. So we have a database, and we log the longitude and latitude, and we say, okay, so 0.2 minus 0.1, it's still American, and then it's a sequel, so with some, so the decimal point is a point. So what's the result here? You've been reading my slides, damn you! No, it's actually 0.1, and here it's actually 1.1. But then you're absolutely right. Here it's here, and of course, the problem is that it's the float precision problem that everybody knows about. I don't know if anybody's as old as me that actually programmed in C++, and you had to compare two doubles. Right? Because it's the same problem. Yeah. Oh well, but I mean, that's what happens if you don't do something about it, right? And it's actually really easy to test. I mean, you can make two small scripts in SQL and run it like this. You would expect that it would stop at 10, right? But first of all, you get these really funky values, and it doesn't. But of course, if you do the decimal thing, then it does. And now, the reason it actually says 10 here is that it's actually SQL Server Management Studio that rounds the value. It's actually not 10 point nothing, but it displays it wrong. So yeah, so it's the float precision problem. And again, you may say, but that's nothing. But first of all, it looks really stupid. I mean, when you print the invoice, and I mean that round. I mean, if you, I worked for like 6 years in an online investment bank, and I can tell you, people were picky, right? I mean, when you're talking pips on the fourth decimal, you don't want something like that. So depending on your business context, a small rounding error can actually be quite faithful. Now, of course, SQL Server has a data type point. That's like a geography data type that you could use if you come into situations like this. But yeah, a couple of years ago, some years ago, it didn't. Don't use floats. Floats are basically for imprecise numbers, right? I mean, that's just the way it is. Hey, we're good on time. So let's then move into an actual system. Because again, I mean, I'm not trying I'm not only trying to scare you off, right? I mean, a lot of good can actually be done in predictive maintenance or anomaly detection, as I prefer to look at it, because then it's not a time series problem, then it's a categorical problem, and from a statistical point of view, it's easier. So if you have customers and you want to go and actually sell them something and bring them business value, do anomaly detection. Don't do predictive maintenance. That's like hard. So a small wind turbine company in Jutland, they have like 280,000 suckers standing around, and this system was built for the offshore division. So this is like the front page. So down, we have different turbines. Out, we have different potential errors. So that's like, and you can see the red one, and I do apologize, I'm actually colorblind. So that's why I put, no. So the red one indicates that turbine A01 has a problem in the PT100 generator, right? And the cloud indicates that a service request has been sent, in this case to Dynamics, but whatever system you have to check that. So a work order could potentially be created, and you could send somebody out to fix it. And there are numerous problems with that, because as I said, some of these suckers out in the North Sea where it's high wind and you have to charter a ship and it's freaking expensive and stuff like that. But that's like another session. The yellow, if we take like 03, meaning that there's a warning. So the system is built, it's not a binary. It's not like either it works or it doesn't. There can be like a progression of errorness in it, right? So the yellow is an error. maybe a warning, sorry, maybe something we should pay closer attention to. And then you can dig in, and then you can say, well, what is that? I have some slides afterward that digs into more details of what this is about, but I thought it would be more interesting to actually show before boring you with all the details. So this is a print so the data scientists spent lots of time looking at data. And what you see here are two things. The yellow line, this one, is what we call a baseline. So that's basically a collection of turbines. It could be the same type, same park, east facing, whatever. So a collection of turbines where we look at the same value. And the green one, that's like the real value for this specific turbine. And you can see the nacelle, that's the how, so it's like the cooling liquid in the nacelle, something not good. Okay, so the model predicted an error around the 1st of March. It was fixed on the 8th. We happened to have a repair crew on site. The cost avoidance of this more than paid for the whole development project. So I say, I'm not saying it can't be done, but you know, do it properly. So this one incident in one turbine paid for everything. This is the architecture drawing. It was built around Service Fabric, so that's a back end. The front end I have. So the idea is that you have all the data coming in from the wind turbine generators. It lands in a SQL server. You may ask why a SQL server? Because they knew SQL. Today, if you ask Microsoft, oh, it would be a data lake, or something strange like that, right? But then you have to teach them data lake, or whatever it is. So SQL server. Hosted in the cloud. Free. And then we have all these different services and actors doing different things. Some of them calculating the models, some of them calculating the baselines, Git. And as you see, at that time, it was just before Microsoft bought GitHub and Studio and stuff like that. But anyway, as I said, using dynamics to actually keep track of when and how work should be done. Let me just skip forward. So the business case was that the company was a joint venture between Vestas Wind and Mitsubishi Heavy Industries. Rumor goes that somebody, the former CEO at Vestas, had spent all Vestas' money, and Mitsubishi hadn't really done very well creating offshore turbines. So that seemed to be like a match in heaven. Mitsubishi had the money, and Vestas had the know-how. So they created a new company called MHI Vestas Offshore Wind, something really easy to. It's now been insourced under Vestas again. Because it was a new company, they didn't have anything, so they had to pay the old company to use the thing. And that cost about $500,000 a year. And it was a shitty system. And I had to call them up when the database was down. So the new hosting was about $25,000 a year, right? And it cost, $250,000 to build it, which, as I said, one incident, it was painful. It's fully automated. It uses Azure Machine Learning to actually execute the models. And in this instance, a model it's a very broad sense. I mean, it can be anything from a simple SQL thing to like 1,000 lines of R. The division was very clear. We provided the execution platform. They were the statisticians. They had the domain knowledge. They knew how a turbine could break down. But we're not domain experts, they were. We used Azure Functions to calculate the baselines. As I said, the baseline is a collection that just shows, because a lot of it is visual. So the idea is the way the work is that the statisticians or the data scientists, they look at the data, they get an idea. Maybe it would be a good idea to create a model around this. Then they create a model and we put it into automation. Dynamics, application insights, and data. The SCADA system, it's an acronym, and I can never remember what it stands for, but it's something like collection for something. So it's just exactly. So it's basically the system that controls the thingy, right? In this case, it's a big thingy, but it doesn't. And this is the wind turbine generator. So the data would flow from there
when it was online into a central. Then we would do like a staging area where we had an Azure SQL database. That's another thing that often when we talk about this, we need to execute models. It's always, oh, we need to do like fraud detection, and it has to be instantaneously, and what if somebody's cheating us? And here we executed the models on 30 days of data. I mean, not when something came flying in, no. So every day, every 24 hours, we executed the 1,000 models, I think it was, looked at the data. Of course, if something had been repaired on the turbine, that created like a new situation. So then we wouldn't go further back than that day. So if 10 days ago, and then 11, 12, so forth, up to whatever, of course, that was configurable. Baselines every 4 hours. Because one of the things, that, and this is just a personal point of view, is that you can create the best system in the world, but if it comes with a checklist of 1,000 or 100 points, nobody's ever going to use it. So what this took was, once the model and the baseline had been created, you needed to update. It was like basically 2 lines in a database, because we don't use nice GUIs or anything like that, right? So you go in and hack the database. So and then it was hands-off. The system found out, this is the model, these are the variables, we download them, we train them. When we're done training, we update the results, etc. All that was off. When you create a new baseline, and maybe I should just go back. So the yellow one is the baseline. So let's say you created it like here 1st of March. Then in theory, you would only have data going forward, right? Because that's when it began to calculate. But the system, to allow the data scientists to have something to look at, we actually initialized it backwards in time. So we took all the data we could, and then we calculated it backwards. The same goes that data is not always available. It is missing. So we kept track of that. So if a new value came, we actually recalculated the baseline for that specific baseline. So we would, because, I mean, if we have like a, 1,000 or 100 turbines, it might not be that important. But some of these groups of baseline groups weren't that big, so it could actually make a big. So that's the automatic recalculation. Yeah, front end, and I didn't do that. I mean, I have a thing with buttons, so I had a really nice colleague who did the nice back end in C#, so Fabric. Yeah, deployment 18 minutes. Again, this is not really to do with machine learning, but we didn't have a backup site. Because why should we? This is not mission critical as such. And if Amsterdam should be flooded, we could spin this up in Dublin in 18 minutes. So the idea of spending money having a live was just ludicrous. And with that, I am done. So okay, maybe I should. Okay, that must be for the next time around. So yeah, any questions, comments? Yes. Oh yeah, okay, yeah. Yeah, that was a long time. Yeah. Yeah, yes, you're absolutely right. It was a question of cost. Because basically they said, I mean, so if they didn't do the experiment, they were basically afraid to give Bob a loan. Afraid, I hope nobody's called Bob here. Because they didn't know if they would get the money back. So if they were just using the, I don't know, expert system or whatever it was they were calling it, they wouldn't. So of course you are right in the sense that should it have been a longer period? Should they have done it, before holiday in summer? I mean, those. But this was, it was better than nothing, and I left, so who knows if they repeated it. So, but from you're of course, from a theoretical point of view, you're of course right. I mean, it may be that it was only the good people who showed up at this specific month, right? And then the next month they were really skewed. But who knows? I mean, it was better than nothing. Yeah. Yeah, I mean, they did lose some money. They were actually surprised that, because, I mean, it's something to do with how risk averse you are, and it turned out that they could probably be less. I mean, they could take more risk than initially because of this. I mean, they had a tendency to say no to too many, and actually losing money, because, I mean, the interest on these loans of like gazillion, right? So you're right. I mean, some loans defaulted, but overall it actually showed that, again, that's a business decision. That's not a mathematical decision. That we could actually be a little more lenient in who we give loans. So it was an important point or lesson to learn. And if they hadn't done this, they would never have known. Yeah. So yeah. So a really good question. So the question is, what about the, let's say, if it's not like completely obvious, what if it's just like shifted? And actually, I mean, if you had studied economics, you would know the difference between adaptive and rational expectations. And actually, and the reason is exactly so let's say the trend is correct, but the level is shifted. How do we catch something like that? Difficultly. I mean, but you're right. I mean, you first of all you need a domain expert. You don't need somebody like me to look at the data and say no. So you need somebody who knows that this doesn't look right. And then again, I mean, you can test also, like, is there seasonality in the, I mean, there's tons of tests you can do, especially if it's like on a time series. But of course you have to know that you have to do the tests. An interesting story, by the way, from the economics context. So it used to be that in economics we only have adaptive expectations, and from there you can actually forever and ever be shifted wrong. Then, oh shit, I can't, Robert something. Yeah, this economics came along and actually invented rational expectations, and then the idea is that you kind of take into account everything you know. He got the Nobel Prize for that, but before, his wife had made a prenup saying that if I divorce you and you within the next 10 years get the Nobel Prize, I want half the prize money. See, that is rational expectations. So, yeah. So, anyway. Anyone else? I know I'm standing between you and lunch, but yeah. Oh, no. Oh, no, hell no. No. Actually, my thesis 30 years ago showed that the last thing you should do was use machine learning to do time series analysis. It sucks unless you have really high frequency, where machine learning, and again, machine learning is like an AI and all that stuff, but where it really excels is category analysis. I mean, putting things into boxes. That's where it excels. It can be used for time series, but it's, I mean, some would argue that you should always use it also for time series, because then it's just going to find the next model. If you crank the hell out of it, you will eventually get blah, 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 right? But no. I mean, you're absolutely right. You should be very cautious. And it actually, at least in my experience, where machine learning excels is not in the field of time series analysis. Simply, and the reason so we have something called OML, ML, and that's not actually machine learning, it's maximum likelihood. And you can actually, from a mathematical point, prove that regression, OLS, that under certain conditions, the OLS estimator is the maximum likelihood estimator, and then you can't do better. I mean, it's simply, from a mathematical point of view, you can't do any better. So why? It doesn't matter what machine learning model you throw at it. You're still not, I mean, you may do as well, but you can't do any better. And then you have the problem about causality and correlation that you don't know if it's this variable or that, right? So use it with cautious, but that was anyone? No. I mean, so where I have primarily used machine learning has been within the areas of like object detection. So I've done a number of projects within manufacturing where we had used video and still images to detect stuff, and it can be anything from potholes in the roads to do people have a hard helmet on in a secure area to looking at the last project is as a German pharmaceutical that has a manufacturer like plant in China, and the plant produces between 5 and 10 blister packs per second, and they need to check that the text is printed correctly, because if you can't read it, you can't sell it. I know it's in China, and I know the wages are low, but you don't really want to have somebody looking at them, right? So in that case, we're actually using video to see, can you read it or can't you? And if you can't, so for those kind of use cases, it's phenomenal. I mean, and also if you want to do like customer churn and all those things, then it's